Okay, we're very happy to have Tudor to give us the part 2 of this topic.
Okay, yeah, thanks for the introduction. Okay, so I'll just begin with a very short recap of where we ended last time. So we said that this Donaldson-Thomas theory provides some new cohomology theories, but before investigating those, I discussed more classical cohomology theories for the Hilbert schemes of points on C2 that will contrast with what happens for the Hilbert scheme of points on C3. So in this case, maybe last time we saw how to compute the Euler characteristic, and there was then I said some words about how one can compute the Betti numbers using this Bialynicki-Birula cellular decomposition. Then the Grothendieck group also follows from this BV decomposition. And finally, when studying the derived category, I said that the problems where one studies the derived category of a space can be split in two. One is decompose it in indecomposable pieces. In this case, it's indecomposable. And then maybe, depending on your interest, compute the K-theory of indecomposable pieces or relate them to other spaces. So in this case, this is equivalent to C to D mod sigma D, to an orbifold quotient. So this is Bridgeland, King, Reed, and Hyman. So now I'll talk about the Hilbert scheme of points on C3. So again, maybe the main difference is that whereas the Hilbert scheme of points for C2 is smooth, the one for C3 is singular. So again, we do not know the number of irreducible components or dimensions of irreducible components. In any case, we can still start investigating the same problems. So for the Euler characteristic, a similar computation goes through. So let's say that we want to compute the Euler characteristic of the Hilbert scheme of points on C3. For C2, we used the action of a two-dimensional torus. So here we can use the action of the three-dimensional torus that acts on C3 and then also on Hilb C3D. Yes. So then S fixed points. So this Hilbert scheme of D points on C3, this parametrizes ideals I inside the structure sheaf of C3. So in the polynomial ring on 3 variables of co-length D. So now the S fixed ideals are generated by monomials. And then similarly, what we did in dimension 2, we can obtain a partition. So in this case, it's a 3D partition or a plane partition. So then one gets what's called a 3D partition. So one takes the complement in the first octant of all triplets ijk, such that this monomial is in the fixed ideal, S fixed ideal. So this way one obtains a 3D partition of D. So then the Euler characteristic of Hilb C3D would be P3D, which is my notation for the number of 3D partitions. So we found the Euler characteristic. Now for the Betti numbers, this seems a very hard problem, or at least not amenable with the current techniques. So by Betty numbers, you mean this periodic cyclic homology? Yes. And then, yes, you can compute them. So the odd one is 0, and the even one, yes. Oh, and yeah, I guess the 0th one is P3D. Yes. Yeah, this is a hard problem, as we don't even know some basic geometry related to the irreducible components of Hill C3D. So instead, I said, one uses a different cohomology theory. So let's call it critical cohomology. So we said that locally, these moduli of sheaves on Calabi-Yau threefolds are given as critical loci of some regular functions. And out of those regular functions, we build this sheaf phi of vanishing cycles. And we said that it's a better idea to study that. That will be easier to study than the constant sheaf that gives the Betty numbers. So in this case, what happens is that the Hilbert scheme of points on C3 is the critical locus of a function W on a smooth variety and Hill D. So now I'll explain the definition of this smooth variety and Hill D and of this regular function W. So yeah, so what happens is that the Hilbert scheme of points on C3, so this parameterizes this point either correspond to ideals inside of calling to D inside the polynomial ring 3 variables or quotient of C x y z of dimension D. So here V is a C vector space of dimension D. We want to parameterize such quotients. So we'll write this space using some linear algebraic data. So it's as follows. So X, the variables X, Y, and Z of this polynomial ring act on the vector space V. So X induces a linear map, also denoted by X, but by capital X and V. And similarly for Y and Z, we get 2 linear maps on P. Okay, so now we just wrote the fact that the V is a representation of the 3 algebra in X, Y, Z. Now, X, the 3 generators of the polynomial algebra commute, so also these linear maps will commute. So X, Y, Z pairwise commute. So also X, Y, Z pairwise commute. But we also have to use that V is a quotient of the polynomial algebra. So let V in uppercase V be the image of 1 under the projection. Then V will generate the full vector space under the action of X, Y, Z. So I'll use this notation. Okay, so the Hilbert scheme of D points on C3 can be described using these endomorphisms of a V that pairwise commute and this extra choice of an element in V which generates the vector space V under the action of X, Y, and Z. So the condition that makes this space singular is this pairwise commutativity condition. So this introduces singularities. So we define a space by removing that condition, by ignoring that condition. This is this non-commutative Hilbert scheme, N Hilb D. So this will be same, parameterize the same data. But without commutativity. So N Hilb D its elements will be tuplets, so it's in V, so this corresponds to this vector, the image of 1, times 3 endomorphisms. But inside this affine space, we select an open that corresponds to this condition. So this open space can be given as semi-stable point with respect to the determinant linearization, and it corresponds to this condition, that V generates the full vector space V under the action of x, y, and z. And then we quotient by the action of GLV, just by conjugation. So the only thing we changed from the definition of Hilbert schemes of points was removing the commutativity condition, and then we can describe it as a GIT quotient. And this quotient is a smooth variety. Now we have the smooth ambient variety. So the next thing is to say how the Hilbert scheme of points on C3 appears as a critical locus here. And the function we consider is the trace of x times the commutator of y and z. So this will be a regular function on N Hilb D. And now the critical locus of W is, so for example, you can expand this trace in the x coordinate, then if you impose the condition that the partial derivatives with respect to those x coordinates are 0, this will say precisely that y and z commute. But you can also use that invariance properties of the trace function. So you can also write it as y times the commutator of z and x, and do the same argument for the y coordinates. You get that those points will also have a property that the commutator of z and x is 0, and similarly the commutator of x and y is 0. So what will happen is that the critical locus of W is the sublocus of tuplets V, X, Y, Z with a property that lowercase v generates the full vector space V under the action of X, Y, Z. And now we also have this condition that X, Y, and Z pairwise commute. So it will be Hilb C3D. Okay, so now instead of studying a singular cohomology of Hilb C3D, we study what is called the critical cohomology. So this is the cohomology of vanishing cycles. on n cube d. Okay. So here, phi is these vanishing cycles. So, we would like to, as I said last time, we would like to get a perverse sheaf as they have a certain good properties. So to get a perverse sheaf, one applies this functor called the vanishing cycle functor, has to apply to a perverse sheaf, which is the IC sheaf on n cube d. So this is just the constant sheaf with a plus a shift. And then this shift will introduce some signs. So maybe I should say, so this is a perverse sheaf supported on the critical locus of W. So it's a sheaf supported on the Hilbert schemes of points on C3, but it is not the constant sheaf. So the picture here. Sorry? Pure. You mean if you apply vanishing cycles for an arbitrary function to a pure? Sorry? For this particular function, if this is. Okay, yeah, I guess. Yes. It is pure if you push it forward to the core space of this matrices. But indeed, it's a good question if it's pure before pushing it forward. I don't know. Yeah, I don't think it's known actually. Yeah. Yeah. So the picture is something like this. So this is, we have a space over the complex numbers. So this is n cube d, which is smooth. So the fiber over 0 is the only singular fiber. Okay, so maybe, so what happens here is that we're interested in this Hilbert scheme of points on C3. So this is singular, but it is also the singular locus of the preimage of 0. And over any other point, the preimage is smooth. Okay. So you're interested in some singular variety, and you write that singular variety as the singular locus of a larger variety that you can put in a one-parameter family. That's the only singular fiber, and the total space is smooth. So now these vanishing cycles, so this phi, so phi measures the change in topology between the generic fiber over epsilon different from 0 and the special fiber. Okay, so maybe before, yeah, I should mention that now one can compute the dimensions of this critical cohomology. I'll just write computed by Baron, Brian, Chandroy, Davison. And one obtains formulas similar to those in dimension 2. Okay. So one way to understand these formulas is to look at the following map. So there is a projection map from N hilp D. So again, this was parameterizing tuplets V. Yes, but no, here they also compute the dimension of individual HI. The whole structure is pure here, but yeah, they compute this for individual. Yeah, maybe it was not clear from my notation. Thanks. Yeah, so when you do the generating series, it will be sort of T deformation of the McMahon. Yeah, so the tool for studying cohomology like this is, for example, a proper map. So in this case, it will be from N hilp D to a space that forgets the framing vector V. It's all denoted by XD. So one studies the push forward of this perverse sheaf phi. And actually one can compute, this will split as a direct sum of simple perverse sheaves, and one can compute explicitly those simple perverse sheaves. So this will be given by sum of what are called BPS sheaves. Various copies of the BPS sheaf in dimension D, and BPS sheaves from smaller dimensions for partitions. Oh, hope I didn't break that. Yeah, so the way one studies this is one first considers the push forward of the constant sheaf or the IC sheaf of N hilp D. Then the decomposition theorem, BBDG, decomposition theorem holds for this particular sheaf. So this will split as a direct sum of perverse sheaves. And then, which can be explicitly written, and then one applies the vanishing cycle functor that will commute with proper push forward. And then one studies the vanishing cycle functor applied to these perverse sheaves, and then those will be the BPS sheaves, and those can be computed explicitly. So this is what I'll mention about this BPS sheaf, BPSD sheaf. So again, this is a sheaf on XD. So XD was GLD plus 3, so triplets of matrices up to conjugation. And inside XD, we have a copy of C3. We consider diagonal matrices, whose image are diagonal matrices of this form, just the multiples of the identity, ABC. So then this BPS sheaf is just a push forward of the diagonal for the IC sheaf on C3. Okay. So what is happening here is that one decomposes this critical cohomology, this new cohomology for the Hilbert scheme of points on C3 in copies of this BPS sheaves that have to do with eigenvalues of this three matrices parametrized. So yeah, also this BPS number is just Euler characteristic of the cohomology of this BPS sheaf. So in this case, it is -1 for all of these. I mentioned these. Yeah. Any questions? Okay, so this BPS invariants, they sort of yet another type of enumerative invariants that are more fundamental than Donaldson-Thomas invariant, for example, or Gromov-Witten invariant. So level Donaldson-Thomas invariants are expected, in more generality, to be written in terms of this BPS invariant. And this kind of computation done here for this critical cohomology is an example of that. So going back to this analogy with Hilbert C2D. Yes. Yeah, so for other partitions, it will be a push forward, certain push forwards from partition. So you have xd1 and xdk in xd by taking direct sum, and then you push forward what is BPS d1 box BPS dk.
What is the cohomological BPS? I thought BPS would be the one that you upstairs on the system, right? I guess it's a question of terminology. Why did you? BPS is something you would like to. The BPS are some sort of invariant for which you would like to GT the symmetric power. So when you want the structure, you probably would like to forget the conductor. And then you go to the diagonal and then the structure taking the methodology. But it's when you, I mean, like you take an arbitrary x and then the two of your weakness and those are expressible by the yes, not the maximum value is supposed to be.
Yes, so they are supposed to be Euler characteristic of those sheaves, of these sheaves. Yeah, but I think it's also it's yeah, I don't think it's known whether this sheaf has any decomposition. This sheaf phi, so it has decompositions after you push it forward to this force space. Okay. So
in general, somehow it's you can also do it in terms of this correspondence between DT and sort of that M theory. In this case, one is always takes like over Chow. Somehow you forget the data, certain Chow. All of that is emotional. You can add the cycle.
Yeah, so this formula here, making it explicit, computes its Betty numbers. So the next thing I want to talk about is versions of K-theory and derived category for Hilbert scheme of points on C3. So it will actually be easier to just talk about the derived category. So the replacement.
Is there a machine to somehow reconstruct the individual inside? Still have that from the different numbers.
Yes.
Suppose you have some more general. Well, you can answer the question in general.
What question? Like the
individual basic number.
Yes, yes.
But there is no way to reconstruct it from some category. From the category, only get it in periodic.
Yeah, as far as I know. Sorry, the Hochschild homology. What? Sorry, what did you say?
Because previously you asked a question about taking the cohomological matrix factorizations, and your response was that it's only just two grades, right? So
yes.
If you take, because you consider the type of
yes.
But if you take Hochschild cohomology, which is reserved directed, will not give
I mean, there is some spectral sequence, this Hodge to the RAM spectral sequence also in this case, but again, as far as I know, it's Z mod 2Z graded. But indeed, you may hope that there is an extra filtration, but yeah, kind of the thing that that's worrying is that if you just have, if you're interested in a variety X, but if you go to the derived category, you look at dBx, out of dBx, you cannot reconstruct the Betty numbers. So because of this, we're kind of expecting this will also happen here. So I never worried about that. But here, kind of the Betty numbers, once you actually have this formula, in terms of BPS sheaves, they are kind of easy to read because this is ICC3, so you know that it contributes in only one dimension, and then you have some explicit shifts. So then you'll get a formula for each individual HI. Yeah. So the replacement of this category of coherent shifts on Q of C3D is given by a category of matrix factorization. So it's DTD equals matrix factorization on n Hill D for the regular function W. So what are the objects of this category? So they are follow. So you take two coherent sheaves on n Hill D. A map from A to B and a map the other direction from B to A. So it's a tuplet of AB, alpha and beta, such that alpha. I'll continue in this other one. Such that the composition of these two maps now it's not zero as it is the case for a complex, but they are multiplications by W. So this is the category that we're considering now. So as I said, it recovers. So this definition, maybe I should have said, so it's of course more general. So here you can put a smooth variety and a regular function on that smooth variety. But I should just say that this MF and hill D, for the case I wrote, recovers this periodic cyclic homology, smooth affine variety. I think it's also one needs to do this curved matrix factorization. So yes, but okay, yeah, smooth affine variety. Then it's exactly the definition that I wrote. Yes. So via periodic cyclic homology, this category recovers the Z mod 2 Z periodic critical cohomology. And in particular, it recovers the DT invariant by taking the dimension of HP0 minus the dimension of HP1. So now the plan is to study this category DTD. And the analysis we'll be using is this sort of two-step analysis. So now we have this derived category, which is associated to hill C3D. We want to see whether it is indecomposable or not. And if it's not indecomposable, ideally you would find the decomposition in indecomposable pieces. And then the second part is to study those indecomposable pieces. Okay, so maybe I'll write the theorem. But I'll introduce some notation that I'll explain after I say the theorem. So
some kind of category with which kind of like circle some space, and then push forward to like a normal space, also right. And then you have something about I don't know, just taking the theory of physics model or something like that, or whatever, some type of thing. And you know how that push forward of that sheaf that is going to push on your horizon. Here you went from triple to X, Y, and Z.
yes, yes.
And then then the homology there was put into
yes,
sum.
yes.
Do you expect in this situation the category also have some kind of composition?
No. No. No, I think, for example, if you take
like in this kind of don't commit to the solution.
Yeah, not even in that case. So even, for example, in that case, if you take, if you want a K3 surface and that will have a map to a singular surface, or if you want more in what I mentioned last time, this Halper-Leisner stuff, you can do this, some moduli, a hyperkähler variety, which is a moduli of semi-stable sheaves, also give a Mukai vector on a surface, on a K3 surface, and then it will have a map for the corresponding space on the wall for a Giesinger stability condition for which the space will be singular. Then you can study push forward for the, maybe I should write here. So this X is hyperkähler, let's say. So something like M L plus semi-stable V to Y, which is M L semi-stable V, which is singular. So you can study F lower star of the IC sheaf on X, and then this will not be the IC sheaf on Y. So it's IC of Y plus other stuff. So I think this will be a semi-small map, and you'll also get other strata. So, however, so maybe your question could be interpreted as categorify the decomposition theorem in this case. But however, dBx has no non-trivial SODs because X is Calabi-Yau. Yeah. 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 So this is now I'll mention this sort of answer, or at least partial answer to the first question. I will introduce some notation that I'll explain. There are categories. Yeah. SDW. Yeah, I'll explain where they live, such that this category, DT category, has a semi-orthogonal decomposition. I'll also explain what this product is. Okay, so it will be some product of these categories, SDI, WI, with the property that D1 plus DK equals D, and that 0 is less than or equal to W1 over D1, less than WK over DK, less than 1. So maybe I should have said here. So here D corresponds to the number of points, but W is an integer weight. So we construct some so kind of the point is that now in dimension 3, these categories will not be decomposable, as was the case for Hilp C2D, where we construct some semi-orthogonal decompositions in terms of these new categories SDWs. Not precisely, right? So I think so. What will happen is that if the greatest common divisor of D and W, then this will correspond to BPSD, a copy of the BPS sheaf. But if this is not the case, then the contribution of this to the formula that this Baron, Brian, Sandra, Davison stuff, the contribution will be BPSD plus some other strata. And yeah, as I was saying in a second, that cannot be categorified in this using this semi-orthogonal decomposition. But it can be categorified if you go to K-theory and you define a coproduct. Okay, so this is what I'll talk about next. So the remark is that, well, maybe not, I shouldn't have said remark, but I'll state a more precise conjecture a little later, but we believe that the categories SDW are indecomposable. I'll actually state a conjecture relating these categories SDW with something similar to this orbifold, but in dimension 3, and such a statement will imply that they are indecomposable. So this will give an answer to this first question.
Sorry, so what is the K?
Yes. So it's the composition after all sums of D, and then you need to choose some weights and such that this slope condition holds. Okay, so I'll have to explain what these categories SDW are, but I'll just begin discussing how one proves a statement like this, and then these categories will pop up there. Okay, so the proof is as follows. So you want to decompose these matrix factorizations for n Hilp D for potential W. So instead, we study semi-orthogonal decompositions when the potential is 0. And we will construct such a decomposition that respects the potential W. So this will allow us to apply matrix factorizations for potential W at the end, and then obtain a statement about matrix factorizations. So kind of maybe an advantage. This is an advantage of working in this categorical framework, that we can just do this simplification. Just worry about the zero potential, but prove a categorical statement, not numerical. And then put the potential at the end.
So to make sure, QP is a bit of a V, a vector in CD, XYZ?
Yes, yes.
No constraint.
No, but the constraint is that lowercase v generates the full vector space. Yes, it's an open number. Yeah. Yeah. So. Yeah. So n cubed d again was v plus and v plus 3, semi-stable inside GLV, and this is inside the full stack. Okay, maybe I'm all right. But then there is a map to XD. So now this is a stack, quotient stack, where we parameterize, where we forget the vector v. Okay. And then the core space of this stack is this variety XD that I considered before, and the variety on which we constructed the BPS sheaf. Okay. So now we'll construct we'll construct an SOD of XD of this stack, and then we'll pull back pieces to n hilde d to obtain the desired semi-orthogonal decomposition. So now, the important thing is this constructing semi-orthogonal decomposition of the stacks. So there are many techniques. So there's many techniques. Yes, yes. This is this is non-trivial. So kind of what will happen here is that the stack will have some large semi-orthogonal decomposition, and out of those pieces we identify just certain pieces that we pull back here, and then they still remain semi-orthogonal, and they also generate this category dB and QD. But the main work is in studying dB of the stack. So there are many techniques for studying dB of smooth stacks, especially this most basic case of quotient stacks. So due to which go roughly under the name of window categories, due to Harper-Leisner. Ballard, Favero-Katsarkov. So these authors decompose coherent sheaves on stack using a stability condition. So they will have some p's that will be equivalent to dB of semi-stable points with respect to that linearization, and then some extra stuff coming from unstable loci. However, in our case for this stack XD, the whole thing can be unstable, but you need some sort of ordering. Instability, yes. So some stratification that behaves like Kempf-Ness, that the push forward, it's an inclusion, and yeah, the closure of the stratum. Yes, that's right. Yes, yes. Yeah, it's a little more general, but still it does not apply for this particular stack. So kind of one problem here is that there are two possible linearizations, determinant and inverse of the determinant, but the semi-stable point for both of them will be the full affine space. But in any case, one can still use their techniques, and actually authors who studied this before and yeah, have many results in this direction are Spenko-Vandenberg. So that is study decompositions for smooth stacks, but beyond the stability situation. Okay, so now okay, so this Spenko-Vandenberg, basically yeah, inspired by their work, one can define some primitive pieces that will generate dBxd. There will be these pieces dBw inside dBxd, such that dBxd has a semi-orthogonal decomposition in mdw for all integers w plus pieces coming via the whole product.
So to make sure your curly xd, there's no xs. Your curly xd, there's no xs anywhere.
Yes, no SS. Yes.
So we do the correspondence space to the naive quotient.
Yes. Yes, it's an affine variety. So this for this X we have a whole product. So it goes like this. So if you have a partition is d1 up to dk, then we can consider a stack of extensions d1 up to dk. I mean, this can be also written as the corresponding parabolic at power 3 mod the corresponding parabolic group, and it has a map to xd. So the whole product is this functor pi lower star q upper star. Okay. So yeah. So again, what I'm saying here is that this stacks xd, they will have these decompositions using some primitive pieces, mdw, and the extra stuff will come via a whole product from partitions, non-trivial partitions of d. Okay. But this mdw well, are not maybe, or may not be. Yes.
And the GLB action.
Yes.
How should I think about this control of such a...
Or if you want, it's GLV equivariant sheaves on an affine space. Or so this may not be geometric. So i.e. equivalent to dB of a variety, which was happening in this window category case when one would have obtained that they are equivalent to dB of a semi-stable stack. So maybe, yeah, but they are what is called non-commutative resolutions of singularities of XD of this core space. So they are smooth categories, but they are also sort of proper over this affine variety, over this core space XD. Okay, so now I ran out of space. Yeah, so this is what I was explaining. Okay, so now I have to tell you how to define this categories MDW. Yes. 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 But it's kind of, I'd say it's very different from the situation, because then you have some unstable strata, and then I think, I don't know, for a given levy, you kind of have you have only one direction in which these pieces will appear. Whereas here you have for a decomposition of D in D, like D1 plus D2, yeah, sometimes you'll have the product D1, D2, depending on the extra ways, W1, W2. In some other situations, they will be the other way. So kind of in this situation, it looks like I'd say it's more like some stable, not only the origin, all stable. But I think in this, like the usual Kepner stratum is that if, let's say, is for lambda, you get an unstable locus, then for lambda inverse, that might not be unstable actually. In many cases, generically, that will be stable if you flip it. But here they come from all directions. So you use lambda for example, you use a decomposition D1 plus D2 to get some summons, but you also use D2 plus D1 for some other weights W. Yeah.
Still a bit not clear the decomposition of D into this sum D1.
Yes.
Like, okay, you have this D by D matrix, you have the blocks.
Yes.
What's the motivation for dividing D into these blocks?
I think you would, I think that there are multiple possible answers. So one would be that kind of, I think you would like to decompose this object, the stack XD. So first you want to see what is the contribution via multiplication from smaller dimension vectors. So sort of an algebra.
Do you want to specify those things?
No. I think maybe the point would be that you just have, out of this XDs, for example, you can construct an algebra, and then you want to see what's the image of smaller dimension vectors. Yeah, I think, yeah, so this defines this is the whole product. So it defines a monoidal structure on the direct sum of this DB XD.
Oh,
Yes. This is one reason. So you have kind of an algebra. You want to see the image, in some sense.
Here you have multiple inputs.
Yes, yes. So you have an algebra which is n-graded. Then you want to see what is the contribution of smaller n's, smaller d's, right? So you look at the d-graded piece. You want to see what's the image of the smaller. Yes. This is one motivation. The other would be just that you want to study the stacks xd. You still want to do this window category. So this Kempness strata. Indeed, you don't have a linearization, but you just ignore that. But then the kind of the way this process goes with stacks is that you have a quotient stack V mod G, and you take a character lambda, then you will have a fixed stack V lambda mod Levi, then the parabolic stack push V mod G. Lambda is a co-character of G. So this is kind of the diagram from GAT. This is so what happens in GAT is that this type of maps will be closed emergence, and this will be an unstable locus. But you could still do the same diagram even if you don't have a stability condition that tells you what co-characters are unstable. Just that the difference is that this map might not be a closed immersion, it will just be a proper map. Yes. Okay, so I think if you do this type of diagrams for the stack XD, you end up precisely with these diagrams that I wrote. So a co-character will correspond to the decomposition of V. Yeah. Yeah, so it's basically the same philosophy as these authors, just that you cannot use their results directly. You need to whatever. But you can still use kind of their techniques and whatnot. Yeah. Oh, I defined the stability, but for n hilde D. So for n hilde D, yes, n hilde D it's GAT semi-stable. You can use the determinant linearization. Yeah. But it's a different affine space. So this is this V plus a semi-stable. You mean n hilde D? It's an open space inside the bundle. Yes. Okay. Yeah. So okay. So now I have to explain the definition of these categories MDW. So these are the sort of main character in this theorem. Because this categories SDW would be matrix factorization, where the summands are in these categories. So they are the category generated by the vector bundles O tensor gamma GLD chi. So chi is a dominant weight. Such that, okay, so maybe I should have said, but also the definition of these categories MDW mimics the definition of window categories of this author. So even if we cannot define them as they do, you can still mimic their definition in the case of the stack XD. Okay, and then in any case, because the stack is symmetric, then you would, these categories are kind of the smallest possible categories we can construct in XD, which are part of semi-orthogonal decomposition. So so the point is that they are as small as possible. And now now I'll write the definition. but it's okay. So it's a little weird the first time you see it, but the point is that they are the smallest categories inside dBxD one can define, such that the condition is that this weight plus rho plus minus W over D, sum of beta I equals 1 to D, is in a certain polytope inside the weight space of TD. Sorry, can you? Oh,
These are multiple vectors weight from J over D.
Yes.
Just the integer vector of length D. So the summation of it, if you just write it 1, 1, 1, 1, 1. And this is the integer.
Does this make sense? Okay, maybe I can make it better. Let's see. This is inside sum I less than J. Okay, so Cij, and then this is so I is in position, minus I is in position I, 1 is in position J, with the property that Cij are between minus 3 over 2 and 3 over 2. This is better. But yeah. Okay. So this is inside the weight space for GLD. So this is the reducible representations of GLD of highest weight high. No, I think actually some of these authors also use the same notation because I kind of because building on their papers, I used gamma. So it's so okay. So. Okay.
Is this like some Donald?
Yes. Yeah. Yeah. Yeah.
This condition, how do I understand the condition?
I think so. Okay. I mean, one reason is that you would like to. One procedure you could do is try to find a polytope inside the weight lattice that generates admissible categories. So you know, for any polytope inside the weight lattice, you could construct the same category, define a category generated by vector bundles. Yes, yes, yes. But then most of the categories will not be admissible, so will not be part of a semi-orthogonal decomposition. Or another way of saying this is that the inclusion functor does not have an adjoint, left or right adjoint, for most polytopes.
I see. Oh, that would be admissible. Yeah, sure.
That's admissible.
Okay.
So this kind of smallest polytope that you can construct such that this is admissible is this polytope. So I think this is one way to think about this. So this is have the sum of positive roots. Yeah. So 3 halves. So a half. So minus 1 over 2 to 1 over 2 It is just that yeah, maybe for any pair ij you take an interval of length 1, and then the 3 comes from the fact that you have 3 loops.
Oh, like size is 3, like some sort of.
You have to sum all. You have to add. Take the Minkowski sum of all repelling waves. Right? That's the origin. And then there's the repelling waves are the root, and there's 3 of them, 3 sets of roots. So it's something about 3.
Yeah, 3 is like coming from the C3.
Yeah, 3 times.
No, C, yeah, for C3 or for end V plus 3. Oh, here.
And rho is the half sum of the
Positive root.
That's also correct. No.
Yes. It is d minus 1 over 2, comma d minus 3 over 2, comma. Okay.
Maybe a naive question. So if I just give you some vector bundle, let's say that is generated, and what do I mean by generate? And why there's no red and red edge line back to this guy?
Well, to generate, you take yeah, all complexes that you can obtain by repeatedly extending those vector bundles.
Okay.
Yeah, I think with the adjoint question is, I think there's no reason for an adjoint to exist, kind of a special property. Yeah, if you just have 2 categories like A and B, I mean, yeah, there's no reason why an adjoint of this inclusion would exist. I think it's very special. Okay.
There's also you can say this is the category. This is the complex that if you take the full vector to origin, that will consist of representation of this
Yeah, I remember thinking about this, and I was confused at some point. But I remember thinking this is true. But then now, yeah, on top of my head, I cannot say whether it is not. But related to what you said, then you can also restrict at the origin. If you know they are generated by this, it's the same as imposing a weight condition for any co-character. So the action of lambda at the restriction at the origin for such a complex is between 2 numbers that you can compute, and they are this window width and all that. Okay, so this category is MDW, and the category SDW is just matrix factorization on MDW for potential W. So this says that you have A, B, and alpha, beta. So this was the usual tuple defining a matrix factorization such that A and B are in MDW.
So here, W can be an integer?
Yes, yes. Yeah, yeah.
So why does the division by P
You mean why did I divide by D over there? Yes, I have this W, then it will consist of weights such that the sum of coefficients is equal to W.
So the different W give you different subcategories, or do they?
A priori, yes, but if you tensor by the determinant, so if you shift by 1, 1, 1, 1, then you see that SDW is equivalent to SD of D plus W. But yeah, okay. So so this is we don't have this much time left. What? Okay, so maybe 10 minutes. So this is the definition of this category SDW. This is kind of how the proof goes. Maybe about this remark that these categories are indecomposable, and also sort of a solution to this second part in an analysis of a derived category is that. Yes.
Who's smaller than who?
Oh, well, yeah, I think there is a way to put an order on that. It's not that easy. Yeah. Well, it comes from the way the semi-orthogonal decomposition is constructed is that this defines some polytope, and then you decompose it for an arbitrary weight will not be in the interior of this polytope, but then you need to take r times this polytope for some given r. So then that weight will lie on the boundary. So then, for any weight you record the r such that it lies on r times this polytope, and then you also need to record the face on which it lies, and then you put an ordering on those things, and then that will give you an ordering on this orthogonal decomposition. So the conjecture is that if n is the greatest common divisor of d and w, then SDW is equivalent to matrix factorizations for C3n mod sigma n, zero potential. So this will be a dimension 3 analog of Brijland-King-Reed-Hyman. So then a corollary using our result is that matrix factorization for C3d mod sigma d for zero potential is equivalent to SD0 is inside the DT category. So in dimension 2, it happened that coherent sheaves on Hilb C2D was derived equivalent to C2D mod sigma d. In this case, we just have a fully faithful functor from one category to the other, but we can, by this theorem, we can also understand the orthogonal of this inclusion. So now maybe I'll just mention some evidence towards the conjecture. Yes.
And there was this story about how I can, instead of sheaves on the surface, I can, some kind of, I can, just quantize that. That instead study sheaves on non-primitive differentiation.
You mean this Bezrukavnikov?
Yes, that's right.
Ah, okay.
So in three-dimensional situation, we don't have a threefold, right? So one can think of moving the DD Koch in the direction of that class somehow. What would it mean somehow? Citing or citing in the relationship, or what does it mean? So is there a way to sort of say that there's got to be some sort of some kind of deformation in the presence of a freeform? What is it that we've done?
Evidence. Wait, just to make sure, you want to define the category, right?
Yeah, that's right.
Or you want, I think it's the same thing as getting this sort of non-commutative algebra deformation of. But I think this will have to do with maybe the existence of some tilting bundle. Is this some that you want to?
You have this two form. You may want to make a variable function useful. Three form. You need some kind of
I don't know. Yeah, but maybe I think it's interesting. Maybe you can explain to me later. Oh no. Yeah. yeah, I don't know.
I just missed the part of where everything is happening. So you define your MD in the current entity, right? But
Yes.
you want to pull back at some point.
Yes.
So you just secretly pull back.
Yeah, I think, yeah, you pull back out.
And everything remains
Sorry?
You put it under the carpet, right?
No, I think so. Kind of what I was saying that happens here is that this stack has some big semi-orthogonal decomposition, and then this variety nHill D. So this is sort of yeah, lives over the stack xd, and then you would like to pull back to nHill D pieces in the semi-orthogonal decomposition. No. So I think some pieces will go to 0. So this stack is just yeah, like it's whatever K-theory, or most of the stuff is larger than for a single variety. So you just identify certain pieces in the semi-orthogonal decomposition that you can pull back fully faithfully here. Then you have to show that those generate the category. It's essentially
all the pieces that you define pull back 9.
All the pieces that I mentioned here. Yes. Yeah.
I think some motivation for why to have a W1 over D1 less than W2 over D2.
Oh, motivation. I would say that this condition just comes from the combinatorics. So you take this zonotope and then you want to stratify the weight lattice of yeah, all the whatever weight space in terms of this zonotope plus translates of zonotopes of smaller dimension. And then, okay, you end up with this condition. This is one answer, but then the other answer that I understood after this analysis appeared is that this type of categories SDW, so they, yeah, their provenience again is this stack. So this has to do with this whole algebra for C2 bidimensional reduction. Even here it's C3. That also has, this algebra also appears as an elliptic whole algebra. So defined using, yeah, constructible sheaves on moduli of vector models on elliptic curves. So then this type of semi-orthogonal decomposition should be also seen for those categories of, yeah, what I said, certain constructible sheaves on moduli stack of rank R, and in this case rank D, and Euler characteristic W, vector models on an elliptic curve. And those stacks have harder Narasimhan decompositions, and they should correspond to this slope condition. This is the more, yeah.
What we just answered the same question is that each fraction has to be between 0 and 1 by construction because of the I. But then the individual fractions you can order because the diagram that you have to use with that order. And the ordering, there is an ordering here. The result is more or less independent of what the ordering is. I mean, that you know, Q pullback, Q push forward. Then if you do it for other ordering of the I, you're going to get something which is not new. You're going to get old stuff.
Yeah, but yeah, but it was.
It's important to find that the fallout with the relation.
Yes.
If you're somehow if you're avoiding this one order, you can express it.
Yeah, indeed, if you do the whole product and the slopes are not in this way, then you will have a map to a whole product where the slopes are in the correct way and the cone is in a smaller piece. So you have a filtration on the semi-orthogonal decomposition using this invariance, and then the cone will be under in that smaller thing. But I think, yeah, I don't know. The way I think of this condition is just if you try to construct the semi-orthogonal decomposition using the techniques I mentioned, and you do that, you end up with this. For me, it's more like a computational. But then indeed, it's very surprising that you end up with some sort of harder Narasimhan condition. And then it was.
Naive question, but how many of this, for given D, how many combinations are the number of partitions?
You mean the summons? No, so it's smaller than that. But maybe, okay, how much time is left? I have 3 minutes. No, I think, no, it's fine. I'll answer this. Yeah, so indeed, it would be great if the number of summons were the number of 3D partitions.
No, it cannot be, right? Because each summon corresponds to related vector. The conjecture you have done.
Ah, yeah. Yes, yeah. Okay, so should I continue that? Yeah, maybe just to say evidence towards this conjecture. Then, okay, instead of asking this derived equivalence, you can ask for statements in K-theory. Then if you just take the Grothendieck group of SDW and of this orbifold, I mean, this Grothendieck group is easy to compute. This is, well, yeah, apparently hard, or at least we don't know how to compute it. Then to simplify the problem, no, not even in K-theory. No, I think that actually it's easier to show this derived equivalence via this whole product and factorization than to compute in K-theory. But then in K-theory, what you can do is you can further simplify the problem in at least 2 ways. You can do equivariant K-theory, because you have a torus using a natural torus that appears here. Or you can do topological K-theory. So we take 2-dimensional torus, preserving, that acts on XYZ and preserves the regular function. So it scales x with just some scalar, y with some scalar, z with some scalar. But the product of the scalars is 1. So then you can look at equivariant K-theory. Also, just computing this, we don't know how to do. But then you can simplify it by taking the localized K-theory. So then we can construct some explicit objects in these categories SDW. So maybe, yeah, also using this dimensional reduction procedure. And then basically we use some results of Negut's about shuffle algebra. So yeah, again, I did not explain this, but these categories under dimensional reduction will also appear in categories of coherent sheaves on the commuting stack. And then those are used to define certain shuffle algebras. So and then, yeah, maybe I'll end with this theorem. So then we find a basis for this space. So I'll just denote it like KTSDW prime. So I'll just say that the dimension of KTSDW prime is indeed the number of partitions for the greatest common divisor of the NW. So then the corollary is that if you take this localized K-theory for the DT category, you find the number of plane partitions for D. So this is sort of a maybe categorical, K-theoretic analog of this fact that the Grothendieck group of Hilp C2D is the number of partitions of D. Okay.
So this guy, the group of messages, this was supposed to be, you think about this kind of with the collage, these are really supposed to be the slope Heisenberg that was.
That's right. Yes. Yes. Yeah. So on if you fix a slope w over d, you can take the direct sum of SDWs with this fixed slope. The whole product will respect that. This would be a categorical realization of the slope Heisenberg algebra. Yeah.
You said everyone towards the conjecture, then you interrupted with some nonsense.
Oh, I think this is, yes, yeah, some evidence, yeah. But this is, yeah.
If n equals to 1, is it known?
No, yeah, I think n equals to 1 is the hardest case in this conjecture. Yes, yes, yeah, yeah. No.
Is it easy to say what the category itself is that like an answer for three-dimensional reduction over the zero?
This category SDW? Oh. Ah, yeah, there is a way, yeah. But it's sort of some sheaves on this commuting stack, so that when you push them forward to the pairs of two matrices, they are generated by vector bundles in that polytope. This polytope. Okay.
You forget the potential altogether.
Yeah, so the kind of by forgetting the potential, you need to do this push forward from this derived stack, the commuting stack, to the smooth stack of pairs of two matrices. No, that's the problem. Yeah, so a functor, we hope to construct such a functor by proving the case when the greatest common divisor is 1, and then doing the whole product, and then showing that the whole product factors through an SN equivariant version. Yes, yes. Yeah, but there is no functor. Yeah. So kind of when n is 1, we have an object that should generate this category, and we should what we have to do, compute endomorphisms of that object. It's very hard. Yeah.
Is there any purification of Calabi-Yau
I think there is only one comment that I know. So there is some paper of Kinjo about some dimensional reduction, and I think he has a section there about some maybe some unconstructible sheaf version also for Calabi-Yau fourfold in some particular cases, but I cannot reproduce it on top of my head. But yeah, I think that's interesting. I'll be interested in that direction. Yeah, so maybe, yeah. So that I say about beyond Calabi-Yaus. Yeah, this semi-orthogonal decomposition, we can also prove it for more general Calabi-Yaus. But as I said, there are some technical difficulties in defining this DT category, but we can prove it when X is a local surface. But then kind of also maybe one motivation for studying this SOD is that, yeah, this is the categorical study of DT theory of points. And then one place where the DT theory of points appears is the statement of MNOP conjecture. So MNOP conjecture is that DT has to do with Gromov-Witten. But then for DT, you need to divide by DT of points. So then what we were also interested in is kind of this is a standard problem in enumerative geometry of sheaves, is vary the stability condition or compare this invariant under change of stability condition. So this change will be, we compared some DT categories with this Pandharipande-Thomas category schema for stable pairs, which are certain invariants that realize this quotient. So then you can just compare the stable pairs with Gromov-Witten invariants in the statement of M and OP. So we also have some semi-orthogonal decompositions in that direction. Yeah.
Maybe you could have said about what if you and Richard have this theory, one thing is they never published. I mean, you have something that's exactly economical. You tell you it's relative to the economical. Then that's still, I mean, certainly new to Calabi-Yau, but I thought they also have this very function business in their creation. You get slightly, you kind of get more moving parts there, maybe because you get this kind of rubber opening. So then a rubber is like halfway between 2 dimensions and 3 dimensions. That was I don't know, 15 years ago, something like that.
So, but they also constructed the Berent function using these vanishing cycles, or I guess the Berent function exists for any scheme, but then you need to show it has a description using vanishing cycles. Oh. Yeah. No, yeah, but it sounds interesting. So maybe just to say, so these categories SDW, we call them this quasi-BPS category, so they are kind of the main player in the story. They are this categorical version of BPS invariants, but as it happens, whereas the DT invariant, they have a nice categorification, this DT category that recovers them. This for BPS invariants, you get sort of multiple categorical versions. So these will be a categorification when the greatest common divisor is 1, but when this is not the case, these categories are kind of larger than the BPS.